This talk addresses the functional anatomy of the central tegmental tract. You can see in this brainstem parasital fresh specimen the tegmentum, and in it a thick band of white matter, which I have now traced. This is the central tegmental tract. I have now introduced a myelin stained specimen of roughly the same area. The arrow points to a band of white matter, which I have traced. As you guessed, this is the central tegmental tract. I have now moved the specimen to the side and drawn 7 lines to indicate level of cuts. The first cut is at the level of the superior colliculi, and it is tilted down, thus cutting through the exiting fibers of cranial nerve 3. Here you can see the specimen so obtained. The arrow indicates to the central tegmental tract, which I have now encircled. Next cut goes through the inferior colliculi and runs parallel to the first cut. In it, the arrow indicates to the site of the central tegmental tract. At this level, the central tegmental tract is indistinguishable from the surrounding structures. Cut number 3 was made using the midbrain pontine junction as the landmark posteriorly, and it was angled parallel to the ones above. In it, you can see the decussation of the fourth cranial nerve, which tells us that the cut is going as desired to the midbrain pontine junction. The new arrow indicates to the central tegmental tract, which, as at the superior colliculi cut, it can be delineated. I have now added a green line representing a different angle cut. The starting point posteriorly corresponds to the midbrain pontine junction, but it is more tilted caudally than the cut number 3. Such a cut produces this specimen. As you can see, it also goes through the decussation of the fourth cranial nerve. In it, you can appreciate the central tegmental tract as a relative isolated structure. Cut 4 runs from the upper segment of the superior cerebellar peduncle to the middle of the pons. This cut yields the specimen we are looking at. You can again see the central tegmental tract. Cut 5 goes from the lower region of the superior cerebellar peduncle to the lower region of the pons, yielding the specimen you can see in this frame. In it, you can see the central tegmental tract. Cut 6 is at the level of the middle of the inferior olive. In it, you can see the site corresponding to the central tegmental tract. Slightly below is cut 7. In this cut, fibers belonging to the central tegmental tract can be traced more anteriorly. Now, I have added a line going through the central tegmental tract, and a specimen reflecting this line will yield a coronal cut through the dorsal brainstem, where we can see the central tegmental tracts. But what is the central tegmental tract? In this frame, I have added an schematic drawing of the central tegmental tract and listed most of the structures we will allude to as we answer the question, what is the central tegmental tract? At the moment, you do not need to read this list. We will address each item as we go along. The central tegmental tract is made of 4 groups of fibers. 3 of them are part of the extrapyramidal motor system. They are the pallido-olivary fibers, the reticulo-olivary fibers, and the rubro-olivary fibers. The 4th group of fibers constituting the central tegmental tract do not belong to the extrapyramidal system. These fibers are the solitary thalamic fibers, and they carry taste signals. We will first talk about the pallido-olivary fibers. The pallido-olivary fibers originate from the junction of fibers from the striatum and pallidium, which form the pallidium tegmental bundle, and join fibers from the zona incerta. These fibers, in their caudal progression, reach the mesencephalon and travel through it to the pons and upper medulla to reach the inferior olivary nucleus. Next, we will talk about the reticulo-olivary fibers. In rats, the origin of the reticulo-olivary fibers is the reticular formation. In human, an additional and larger component of the reticulo-olivary fibers arise from the central gray. The reticulo-olivary fibers end up in the inferior olivary nucleus. The reticular fibers are a chain of short reticular neurons that, departing from the reticulo-olivary tract, reach the anterior horn cells. In this frame, I have traced the course of the reticulo-olivary fibers from their dual origin to the inferior olivary nucleus. Next, we will address the rubro-olivary fibers. These fibers run a very simple course. They originate in the red nucleus, as you can see here, and end in the inferior olive. In this frame, I have traced them. These fibers are probably the most studied fibers of the extrapyramidal group of fibers that constitute the central tegmental tract. Why is that so? For 4 reasons. Number 1, the rubro-olivary fibers are part of a circuit that is called the triangle of Gillian and Mollaret, also known as the dentato-rubro-olivary pathway. As you can see in this drawing, the rubro-olivary fibers travel ipsilaterally as indicated by their name from the red nucleus to the inferior olive. Another leg of the triangle goes from the inferior olive to the dentate nucleus, reaching the cerebellum through the inferior cerebellar peduncle. Some authors argue that these fibers make a pit stop at the cerebellar cortex prior to reaching the dentate nucleus, but most authors do not represent this stop in their representation of this pathway. The last leg of the triangle go from the dentate nucleus to the red nucleus, closing the circuit. These fibers travel through the superior cerebellar peduncle. The second reason the rubro-olivary fibers are the most recognized fibers traveling in the central tegmental tract has to do with history. The dentato-rubro-olivary pathway, a leg of which is constituted by the rubro-olivary fibers, was described in 1931 by two of the most famous French neurologists, Dr. Georges Charles Guillain and Dr. Pierre Mollaret. The third reason is that, as it was noted by these doctors, a lesion affecting the rubro-olivary fibers produced very puzzling findings. Palatal myoclonus, as you can see in this 8-second video. Oculopalatal myoclonus, as you can see in this video lasting 25 seconds. And oculopalato-pharyngeal myoclonus, as you can see in this 35-second video, first in the eyes, now the myoclonus in the palate, and now the pharyngeal myoclonus. The fourth reason is that typically 4 to 6 months following a focal lesion in the rubro-olivary fibers, the ipsilateral inferior olive nucleus becomes hypertrophic, as you can see here. This hypertrophy results from transsynaptic degeneration. In this pathological specimen, we can see unilateral enlargement of the left inferior olive. The right olive has a normal architecture. The architecture of the pathological olive, reflecting the phenomenon of transsynaptic degeneration, is characterized by neuronal cytoplasmatic swelling and vacuolization, as well as hypertrophic astrocyte and increased gliosis. Now that we have talked about the famous rubro-olivary fibers, let's wrap this up by talking about the solitary thalamic fibers. The solitary thalamic fibers connect the upper portion of the solitary nucleus, where taste fibers arrive from the tongue, with the thalamus. These fibers carry all taste modalities from the ipsilateral half of the tongue. In this frame, I added the section of an MRI of a patient with loss of all tested qualities of taste on the right side of the tongue. As we can see, the arrow points to a lesion in the central tegmental tract. One more thing about the central tegmental tract: in the MRI of some children, some with and some without neurological deficits, sometimes you find bright signal in the central tegmental tracts, as indicated by the arrows in this frame. The significance of this finding is unknown. Thank you very much for your attention.